All right, moving on to 6.6. We are kind of moving away from the type of figures that we've been talking about. So far, we've been talking about four-sided figures called parallelograms, and we looked at rhombuses or rectangles, and squares. Okay, remember the deal with rhombi are that they have all sides congruent. We talked about rectangles and they had the right angles. And then we talked about squares, which had both of those things. Last section we talked about how to prove the figures were not only parallelograms, but rhombi, rectangles, and or squares. And now, like I said, we're going to be moving away from the type of figures we've been looking at. Just to look at a Venn diagram one more time, you guys probably remember, well, we're in geometry. We started looking at shapes. After we looked at shapes, we started talking about shapes that only had straight sides, were closed and two-dimensional, and those were called polygons. After we talked about polygons, we got a little bit more specific type of polygon, which was a parallelogram. Then we talked about rectangles. We talked about rhombi. It's hard to read. And then we talked about squares. All right. Now what we're going to be doing is we're going to be looking at different polygons. I probably could have also drawn another box here, and that box would have been called, all of these things that we were looking at were quads. Now, a parallelogram is a quad, rectangle is a quad, a square is a quad, a rhombus is a quad. Now we're still going to be looking at quads, but none of them are going to be parallelograms. We are going to be looking at a figure called a trapezoid. Okay, and then we're also going to be looking at a figure called a kite. You can see how that fits inside of our nice Venn diagram here. So, what is a trapezoid? A trapezoid is going to be a quadrilateral with exactly one pair of parallel sides. Okay, so it has to have exactly. If it has two pairs, it's not going to be a trapezoid, it's going to be a parallelogram. So if it has exactly one pair of parallel sides, obviously they're opposite sides, then it is going to be a trapezoid. Okay, so if we look at this figure right here, these would be your parallel sides right here. Now the legs are going to be the non-parallel sides. So that's a leg, that's a leg. The bases are the parallel sides. So you can think of that as like base 1, and this one down here is base 2. Or the other way around, it doesn't really matter. Just know that the parallel sides are going to be your bases. Now the base angles are going to be the angles between, that means between the base and the legs. So here, this one and that one would be one pair of base angles, and up here would be another pair of base angles. Now what do you think isosceles trapezoid means? What is isosceles triangle? It's a triangle with two congruent sides. Exactly two congruent sides. So an isosceles trapezoid would be a trap with congruent legs. That one is congruent to that one. And these would be your parallel sides. All right. So if we look at this, it says if a trapezoid is isosceles, then what? What do you think is true? What is something we know about isosceles triangles? Isosceles triangles, we know that those are congruent, which tells us that the base angles are congruent. If a trapezoid is isosceles, then the base angles are congruent, which means that will be congruent to that, and this one will be congruent to that one. The two pairs of base angles will be congruent. And not only that, but don't forget, the two bases are parallel. So we can also use the fact that these are same side interior angles and they're supplementary. So these ones are going to be congruent, and then these ones are going to be sup, and those are going to be sup. So we're going to use all those things when we're trying to figure out missing angles. We're looking at this right here. Those are base angles, and this is an isosceles trapezoid. So we know they must be congruent. When things are congruent, you can set them equal to one another. They're measures. So 2x has to equal 70. Therefore, x equals 35. How about this one? How do we, this isn't like a parallelogram where we know the opposite angles are congruent. So how are we going to work through this? Well, we know these angles are SSIA, so they must be supplementary. So they must add to be 180. If you already have 120 accounted for, then this one must be 60 degrees. And then these are base angles of a isosceles trapezoid, so they must be congruent. So that must be 60 degrees. So once again, you have your SSIAs, and then you have the base angles being congruent, which comes from this theorem right here. On here, we kind of need to jump around. This one's 140. I'm going to do the supplementary angles first. So I'm going to figure out what this is over here. They must add to be 180 because you have SSIA. So that's going to be 40. If that's 40, then what's this one going to be? 40. And these come together to make a line. What's that term for two angles that come together to make a line? Linear pair. Linear pairs are sup, which means they add to be 180. So if this is 40, then this one over here must be 140 degrees. So you can kind of jump around these figures a bit. Right, let's move on. Okay, now the next thing that we're going to look at here is talking about if we know that it's an isosceles trapezoid, then something is true about the diagonals. I went over and I drew this diagonal, and I drew that diagonal. Does it look like they bisect one another? No, they're not bisecting one another. They're not cutting each other in half. Does it look like they're perpendicular? Doesn't seem to be perpendicular, especially if we made this side come further out, because then they're even further away and they're not going to intersect perpendicularly. Does it look like they are? They seem to be congruent. All right. As I've told you, we will not be doing a lot of full-on proofs, but we will be talking through proofs. So let's try to figure out how we could prove that those were going to be congruent. Well, basically, we're going to be looking at this triangle, and I wish I could change the color, but I'm going to just overlap them. So it's those two triangles which are usually sitting on top of one another. By definition of isosceles, those are congruent. By the reflexive property, these are congruent. And what do we know about the base angles of an isosceles trapezoid? They're congruent, so that must be congruent to that. So why are these two triangles congruent? SAS. And after SAS, how do we know that this is congruent to that? CPCTC. Since it's been a long time since we've done a proof, I do want to go over and do one occasionally. So let's go ahead and write this down. We know that figure ABDC is isotrap, given. Okay, So then we know that AC is congruent to BD. Why? Depth of isotrap. We then said that CD was congruent to CD because of the reflexive prop. We finished it up. There's other ways to do this proof, but this is probably the easiest way. We said angle ACD is congruent to angle BDC. We can call it the base angles theorem of traps. Then we knew that the two triangles were congruent. Triangle ACD is congruent to triangle BDC. That was because of SAS. And then we could say that AD was congruent to BC by CP, All right, more work with trapezoids. The midsegment of a trapezoid is this, just like the midsegment of a triangle. It is going to be the segment with endpoints at the midpoints of the sides. So, and this is going to be working with all trapezoids, not just isotraps. Now, if we look at this right here, what is one characteristic that seems to be true? The midsegment seems to be parallel to both bases. Now that we know we have that parallel shenanigans, I can throw in a million things having to do with parallel as little side problems. Other than that, this is weird, because this is like a short side and this is a long side. What do you think that is? Because from being short, as it's moving down, it's getting longer and longer and longer and longer and longer and longer until it gets to being the long side. So what do you think is true about the midsegment? It's going to be the average of the two bases. It's obviously not going to be equal to the short, it's not going to be equal to the long, and it is the length when it is halfway between the short base and the long base, so it's going to be half of that. Okay, so if you wanted to know that, it would be the midsegment, I could call that M, equals base 1 plus base 2 over 2, just the average of the two bases. Would that work for a triangle? Well, we know that a triangle, that was weird, because a triangle, this thing is half of the base. Let's see if this works. Midsegment equals base 1, which is the base, plus base 2. What is the length of this thing up here? 0 divided by 2. Yeah, same exact formula. It's just the base divided by 2. Because for a triangle, the second base is just 0. So this formula is technically the formula for trapezoids, but it would work for a triangle as well, just knowing that the base is 0. It's trying to figure out the web of all of the material we cover. It's best to not memorize this, but understand it via a web. All right. Now let's move on and try to use this information. So if we looked at this, some of you guys can do this in your heads. The short is 10, the long is 70. This is going to be halfway between those two. So what's it going to be? Too hard for me. I'm going to do it using the formula. It is base 1 plus base 2 divided by 2. 80 divided by 2, it's 40. And that should make sense because going from here to 40 is adding 30. If we add 30 from that 40, do we end up with the other side, the other base? Yep. If we wanted to use that same logic here, and you ask, how do I get to the midsegment? That's adding 30. So how do we go to the other base? Just add 30 again. That's the way you could do it just in your head. The other way is by saying midsegment equals base 1 plus base 2 over 2. So midsegment, in this case they gave it to us, 50 equals base 1, which I don't know, x, plus base 2, 20 over 2. And you guys should remember how to solve these equations from Algebra 1. Multiply by 2 on both sides, you get 100 equals x plus 20. And when you subtract 20 from both those, you get your 80, which is the same thing we got when we did it in our head. I can't read this at all. I can't read that. Let's try to make it. It might work or it might not. 4x, let's call it plus 10. I don't know if that's going to work or not. And then x plus 2. And then let's call this 60. Let's see if this works. Okay. So we know that the mid-segment, x plus 2, equals your first base, which is 60, plus your second base, which is 4x plus 10, all over 2. And we're just going to solve this. Multiply by 2 on both sides. 2x plus 4 equals 4x plus 70. I think we're going to end up with a negative number because I couldn't read the actual numbers. All right, let's solve it. Minus 2x, that gives us 2x, minus 70, negative 66. Get x equals negative 33. Obviously, this makes no sense. It's just because I could not actually read it, but I wanted to show you how you would do this. Notice how I multiplied by 2, and then I didn't forget to distribute, and then I went from there. All right, that's all we're doing with trapezoids. Let's move on to kites. Remember, we talked about a trapezoid has exactly one pair of opposite sides being parallel. We talked about an isotrap when those are congruent. Now, let's go on to kites. What a kite is this figure over here. A kite is going to have no parallel sides. Okay, so this one is going to have no parallel sides, and it is going to be a quad with no parallel sides, and that's an and symbol, sorry, 2 pairs of adjacent congruent sides. So these 2 are going to be congruent, and these 2 are going to be congruent, but they're not going to be congruent to all to one another, or else it would be a rhombus. And a rhombus is a parallelogram, and this says it's not allowed to have parallel sides. So a kite, just like a kite you'd fly in the air. A little string coming down, you're all excited. Okay, now let's look at all the things we know about kites. These are the characteristics. That is the definition of kite right there, but let's go ahead and just draw in the diagonals and see if we notice anything. Okay, one of the things looks like they intersect perpendicularly. Another thing is that these angles will be congruent, these angles will be congruent, and these ones will be congruent. Another thing that's true, if you went over and drew that and that will be congruent to that. This one will not be congruent to that one, but these will be congruent. And then remember, we already had definition. Now, let's talk through the proof. We're not going to actually do the proof, but especially like this one. If we had a kite, definition, those are congruent, and these are congruent. If you drop this down, we have the reflexive property. So triangle 1 and 2 are congruent. Therefore, by CPCTC, those are congruent. By CPCTC, these are congruent. By CPCTC, those are congruent. Okay. Now, over here, now that we know that, we could look at that triangle and this triangle, 1 and 2. How do we prove that these things are congruent? Well, by definition, those are congruent. By reflexive property, those are congruent. And we already proved that that's congruent to that. So those triangles are congruent by SAS. Therefore, this is congruent to that by CPCTC. Okay. This one is the same concept, but now we know that those angles are congruent, and we also know they're a linear pair, so they are supplementary. What's the only way that they can be congruent and supplementary? They're both right angles. So all of this can be backed up by proofs, and all your proofs would have to do with showing a triangle is congruent to a triangle and then using CPCTC. We're not going to do all the proofs, but as I said, the logic behind it we can use without actually having to take the time to write a two-column proof. Okay, let's take a look at this. All right, so this just has to do with kites and those angles. With the characteristics that we already had here, remember these things, okay? Especially this one, super important. So let's look at this. We already learned that those are congruent. So if this is 52, that one's 52, then angle 3, measure of angle 3 must be 52 as well. The diagonals went over and intersected at what angle? 90 degrees. And then lastly, if we knew this was 52 and this was 90, then what's this going to be? What theorem are you going to use? Triangle angle sum theorem. 180 minus the two angles you already have, and you get 28. 28 plus 52 plus 90 equals 180. Does it? Or is it 38? 90 minus 52. 10, 9 becomes an 8. Oh, no, it's 38. 38. Okay. All right, over here, if this one is 36, then what's 3 going to be? Measure of angle 3 is going to be 36. What's measure of angle 1? How do they intersect? 90 degrees. And if we wanted to work with this triangle, that is 36. This is 90, so what's left over? Take away 90, take away 36, and we end up with 54 degrees. 54, 69, yeah, 54 degrees. Now, if this one is 54, then what's this one over here going to be? 54 degrees as well. That could also be thought of as the base angles theorem, because we knew that that's congruent to that, so the base angles would be congruent. All right, let's wrap this puppy up. This is the information we learned today. The mid segment is going to be parallel to the bases, and the average of the lengths of the sum of the bases, or it's going to be, sorry, 1/2 the length of the sum of the bases, aka the average of the bases. The base angles are congruent for an isotrap, and the diagonals are going to be congruent for an isotrap. If you ever forgot that, you just draw yourself an isotrap. Diagonals, that length and that length seem to be congruent. If you didn't believe it, you could do a proof in your head. Now, just to wrap everything up, just remember, a four-sided figure is going to be called a quadrilateral. Okay? If that quadrilateral has two pairs of parallel sides, it is a parallelogram. If that parallelogram had right angles, it's called a rectangle. If that parallelogram had all sides being congruent, that is a rhombus. And if it had both of those characteristics, it's called a square. Now, if it only has one pair of parallel sides, that is called a trapezoid. Your trapezoid, if it has two sides being congruent, the legs, it's an isotrap. And then lastly, what is the quad that has no parallel sides but does have two adjacent pairs of congruent sides? Kite. This all could be written as a Venn diagram as well. I talked about that at the beginning of this lesson, but there you go. This is pretty much going to finish up our study of the different types of quadrilaterals. Lots of parallel sides, some parallel sides, no parallel sides, and these are all the special quadrilaterals. All right, thanks for watching.